Hello everyone. In this video, I'm going to show you some of the choices you can make when creating a free body diagram to represent a real body or system. So here's a real design problem that most engineers will face at least once, if not more, in their careers. So designing a diving board to support a pig. So the design question may be, how long should the board be to support the pig? Or what material to make the board out of? To answer this question, you want to do some analysis, and that analysis probably entails making a mathematical model that can relate the parameters. So if we say, how long do we make the board, then we will probably want to get some relationship between the length and probably the weight of the pig, say. All right, and so in doing this analysis, we want to create a free body diagram. All right. As one of our first steps in doing this. So I'll show you some of the options that you have when you're actually creating the free body diagram. I'll show you 3 examples. All right. So the first example is, I'll call this one 3D. So we'll try to get some accurate representation spatially of the board. Show the thicknesses, show the lengths. My second example, I'll call this 2D with thickness. So I may not care so much about what is happening along this direction, and so I may try to find a simpler model. This, a side view. This is a side view. And in some case, maybe I can use even a much simpler model, so I'll call this 2D, no thickness. And essentially to represent this as a line. Okay, so I'll call this a line model. Okay, so in these cases we've defined the boundary and we've defined what's inside and what's outside. So the next thing we have to define is the interactions. So in this case, the biggest question you're going to have to ask yourself and answer for yourself is, what is the wall or what is the fixture doing? That's the fixed end where the board is attached to some structure. What is the wall, or I'll call it a wall or fixture, doing? We have to translate the actual physics of that structure here into some mathematical representation. And for the purposes of this example, I'm going to assume that the end of the board is what's called fixed. And fixed meaning specifically in terms of mathematics that the end is no translation. So the end does not move. There's no rotation. The board is not going to rotate at that end. All right, so this is the fixed end here, and in this drawing I'll make the fixed end here on the left-hand side. All right, so interactions. This is what I'm going to decide to do. So what do we have to include? Well, the pig is standing on it. Perhaps in this case we'll have 4 normal forces. Perhaps they are different. For the contact of the pig standing on the board, there's the weight of the board itself. In this case I'll choose to just represent it as a series of arrows, and I'll just call this weight per unit area, acting on the bottom surface, uniform over the volume. And then I'll have some reaction forces at the ends. So I'm going to put some reaction forces here. And I'll call those R, Y, in the Y direction. So that's going to give my, assuming that I'm going to take X along the length of the board and Y in this direction. And so let's put this in the field of gravity. Of course, that's where we're going to have the weight, effect of the weight. So I'm going to put some forces here, and I'll call these Rx. I guess we should call those I, because there are various ones. So no translation means that we're going to have to keep it in place. So we're going to have to apply a force, and this is going to be called a reaction or a constraint force. So I'll say R is a reaction from the fixture to the board. And in this case, forces prevent translation. And then moments, and I'll put a moment here, and we can have a distributed moment. It's getting a little messy here, but we'll call this M, we'll call this Z. Z is coming out of the page. So we have X, Y, and a three-axis system at Z, where Z is pointing out of the page. These arrows are curving around the axis, which is around the Z-axis. So the moments are coming out of the page, and we have a series of those. So moments prevent or cause rotation. So we've specified no translation, no rotation. We have forces to constrain the motion, displacement, and we have moments to constrain the rotation. So on our two-dimensional system, we have similar things. In this case, I'm going to make a simplification here. I'm going to call force of pig just one. I'm going to lump these all together. So lumping means I'm just going to group them together as one force using our principle of equivalent forces. I'm going to represent the weight here per unit length this time because I'm in 2 dimensions. And likewise here I will have a single reaction force in the y direction, in the x direction, and then a moment. And I'll call A as this end. So this end here I'll call point A, somewhere here. And so that's the moment about an axis which is passing through point A. It's a single moment. Now on my third free body diagram, which I don't consider the thickness, I'm going to maintain this force here. Here's a single force of the pig. In this case, I'm going to collect all the distributed weight force and apply it in just one location on this pig. And then I'll retain these forces as well. I've used Z in the Z direction about point A. So there's the free body diagram that I can use to do some modeling and calculations and analysis to answer my design question.